Hello, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration units. And I'd like to thank the NASA Engineering and Safety Center and Dr. Curtis Larson for sponsoring this series of webinars. In our previous unit, we were talking about power spectral densities, and we went over a little bit of the theory and some of the background as to how the calculations are done, and we also looked at specification formats as well. In this unit, we're going to be practicing calculating power spectral densities, and we're going to use both measured time history data as well as synthesized data that we generate on our own. So here's a white noise time history that we're going to start off with, and the amplitude, it could represent acceleration in g or some other metric, and that's the y-axis. The x-axis, we have time in seconds. And this particular white noise time history, it has a 1g standard deviation. Now the mean value is also going to be equal to 0, so the RMS value will also be equal to 1g, which is the standard deviation. The duration is 10 seconds with 1,000 samples per second and no low-pass filtering used. Now, from our previous webinar units, you should remember how to synthesize a white noise time history. So if we go to our vibration data GUI package, and we're going to call that up, and this is up to version 4.7 now, we can go to Generate Signal, Begin Miscellaneous Analysis, White Noise, Duration 10 seconds, Standard Deviation 1, 1,000 samples per second, that's just for this example. No low-pass filter. We calculate, and this one will be a little bit different or slightly different from the one on the slide due to different random number seed effects that occur, but it still has the same overall properties. And then we can output this to, or save it in our MATLAB array, and I'm just going to call this white 10 because it has a 10-second duration. So I'm just going to save that internally to the MATLAB workspace. And we're going to come back to that shortly. So the next thing we're going to do is we're going to calculate a power spectral density for the time history. And for the one that's already in the slides, here's the result. So power spectral density, the y-axis is acceleration in g squared per hertz. Now that's really GRMS squared per hertz. That's the true unit, but it's abbreviated as g squared per hertz. Then the x-axis is simply frequency in hertz. So here's the resulting power spectral density. The GRMS value is approximately equal to 1, and the standard deviation is equal to 1. And this is a case where there's zero mean, so GRMS and standard deviation should be the same value. And because of some minor imperfections in the PSD calculation process, this is falls very slightly short of being the full 1 that it should be, but that's okay. So what we've done in this case, now as you recall from our previous unit, every time we convert a time history to power spectral density, then we have to make some decisions as to how to process the data. And in this case, we chose 512 samples per segment, and that corresponded to 38 degrees of freedom with a delta F, that's the frequency step or frequency increment, of approximately 2 hertz. And this had both the mean removal and handing window option selected. So we can actually do this within the vibration data software. So we had our signal generation where we generated our white noise time history, and then we saved that. I can save it again, it won't hurt it. Hit return, and now I've got to go back to the main vibration data GUI menu, the main page. So here we have an option, power spectral densities, PSDs, and spectral densities various. We're going to click on that, and then we have 3 different choices, and today we're only going to be doing the power spectral density. Let's click on that. Now let's read about this. This is version 1.4. This script calculates the power spectral density of a time history, and the input array must have 2 columns, time in seconds and amplitude. So let's do array preloaded into MATLAB, and we'll say it's acceleration in G's. Now our input array name, that's white 10. That's what we already generated. Mean removal, yes. Turn on handing window. we're going to plot from 10 Hertz up to the Nyquist frequency. The Nyquist frequency is 1/2 the sample rate, so that'll be 500 Hertz because our sample rate's 1,000 samples per second. We're going to view the processing options. And this is the biggest decision that needs to be made in calculating the power spectral density is how do we want to calculate it? We could do, for example, we could just do one segment. Now, the numerical engine that's actually embedded in the power spectral density is the fast Fourier Transform calculation. So we want to have a time history with 2 to the nth points where n is an integer. Of course, that may mean we need to truncate, as is the case shown here, because we can get 8,192 samples per segment with one segment. And that will cover 8.1920 seconds. So we're going to lose about 1.8 seconds worth of data because we have to truncate it to make our fast Fourier transform. And again, this is a case where we're just getting the largest segment possible we can with only one segment for our data. So the delta F is the reciprocal of the time per segment. So it's about 0.1221 Hertz. And we have 2 degrees of freedom. Well, we're not going to do this case because we want to smooth out the data and we want to increase the degrees of freedom. And as we increase the degrees of freedom, then we have more confidence in the reliability of our estimate of the true PSD levels, the g² per Hertz levels. And that kind of ties in with something called a chi-square distribution, which you can read about on your own. So let's do the case. We're actually going to do the case with 512 samples per segment. Okay, 512 samples per second. And that will give us 19 segments. Each segment will be about a ½ second long. So our delta F, which is the reciprocal of the time per segment, is approximately 2 Hertz. We get 38 degrees of freedom. So that's going to be choice 5, and we actually have to go over here to click on that choice 5. So let's see, and then we're ready to go and calculate the power spectral density. So cumulative RMS, we're not going to be so much interested in that today. Maybe some other day we will. Here's the time history again. That's the one we generated or synthesized. And here is the resulting power spectral density for this case. Now, this is white noise, and ideally it should just be a flat line, flat horizontal line. There is some variation from point to point, so we have some peaks and some valleys, but you know, that I guess that's okay for now. But what we're actually going to do is we're going to do another PSD, and we're going to select a case where we'll have a wider delta F, and we can accumulate more statistical degrees of freedom. Now, I'm not actually going to demonstrate that for you now. We're going to go back to the slides. Mainly, I just wanted to show you how to do a sample PSD calculation using the vibration data GUI package. But let's go back to the PowerPoint slides now. So here's the power spectral density we looked at before of the white noise time history as shown in the previous plot before this. So let's see what we need to do next. What we're going to do is we're going to reprocess that time history, only we're going to have a wider delta F and we're going to have more statistical degrees of freedom. So let's see how that turns out in the slides. So here's a case here. We have 128 samples per segment, and this corresponds to 156 statistical degrees of freedom. The delta F, the frequency step, is 7.8 Hertz. And what you should see is that this tends to smooth out the data somewhat. So we have more confidence in the reliability of our estimates of the true g² per Hertz levels based on the theoretical chi-square distribution. And of course, this is a power spectral density plot with y-axis g² per Hertz and x-axis frequency in Hertz. So the next plot, now this is going to also be a PSD. I'm changing the format to linear just to make it easier to show my point here. So the y-axis is still g² per Hertz, which is really grms² per Hertz. And the x-axis is frequency in Hertz. Now we've got the blue line here. We've got peaks and dips. And this was the data we looked at previously because it has the delta F of almost 2 Hertz and it was either 38 or 39 degrees of freedom, whatever that number was. So you can see the blue curve is kind of choppy. Now we come along, we use a wider delta F, we get more degrees of freedom. That's the red curve. So you can see we're kind of doing a smoothing out, kind of a smooth average of what the power spectral density is. So again, with the red curve, we have more confidence in the reliability of the data. The trade-off is that our spectral resolution is now wider, it's more coarse. That may or may not be okay. If we're doing a shaker table test where we're trying to demonstrate compliance to a nominal PSD specification, this would be a random vibration test, broadband random vibration spec. There's a nominal level and there's tolerance bands, and we want to produce a plot that shows there are no exceedances above the upper tolerance band, wherever that might be, and there's no dropouts below the lower tolerance bands. So what we like to do when we're doing our shaker table test is we like to use as wide a delta F as we can possibly justify to smooth things out so that the resulting plot is in order. And that way we do not cause any consternation or anxiety amongst the quality control engineers that review our test data who might not quite understand all the intricacies of random vibration data as we do. So we want to save paperwork and all the waivers or consternation that might occur if either we have an exceedance or a dropout with respect to our tolerance bands. And the fact is, knowing other things that we know about structural response to random vibration, including some things we haven't quite learned yet, but we'll cover in future webinars, we know that we can live with the blue curve. If that represents our real data, we can live with that and be confident that that meets the intent of our specification. But our output plot we want to have is the red curve, just so we get a better plot. But there are cases where we want a smaller delta F. We need more resolution. If we're doing a modal test, that's spelled MODAL, and we need to identify lightly damped low frequency structural modes, for example, then we need a smaller delta F, and we're willing to sacrifice degrees of freedom to identify those narrow spectral peaks. So just keep that in mind too. Okay, now another thing we can do is we can convert our data into octave bands, octave band formats. We've talked about octaves earlier in this series of webinar units. So here's the formula between two adjacent frequencies. These could be you could have two side-by-side frequency bands, and F2 could be the center frequency of the higher band, and F1 could be the center frequency of the lower band in terms of their respective frequencies. So we take our lower frequency, we multiply by 2 to the nth power, and n is typically it could be 1, 1/3, 1/6, 1/12, and that will give us the next frequency, the adjacent frequency. So one of the ideas about this format of a frequency step is it's sometimes called a proportional bandwidth. So the bandwidth itself increases as the band center frequency increases. And we'll come across different cases in future webinar units. For example, if we're doing an acoustic sound pressure level, that will typically be expressed in 1/3 octave band format. And for those of you who may have had piano lessons or may have been maybe musicians, well, what we do is if you count the white and black piano keys, that's a 1/12 octave band separation on the piano keyboard. And then when we get to shock response spectrum, then we're going to typically use maybe 1/12 octave format. That's in an upcoming webinar. So let's actually do this exercise ourselves. And I'm going to show you how this works. So if we go back to our power spectral density option, this is in our vibration data GUI script. Do begin analysis, and we're going to call in white 10. Okay, that's preloaded into MATLAB, and actually I need to fix a little minor bug here. Okay, that's on my to-do list, fix that minor bug. But this is our 10-second white noise time history that's preloaded into MATLAB. We're actually going to do case 1. Now case 1 is going to only give us 2 degrees of freedom, and we're going to have a delta F of 0.1221 Hertz. Let's go ahead and calculate that PSD, ignoring the cumulative RMS. So here's what happens if we only have our 2 degrees of freedom and our delta F is 0.1221 Hertz. This PSD data is very choppy. It's very rough. There are peaks, there are dips. Again, for idealized white noise, this should just be a flat horizontal line. But there's something else we can do here, and it's a type of a smoothing method in terms of octave bands. So I'm just going to call this white 10 PSD, and I'm going to save that array. And I'm going to go down here, convert to octave format. So let's do white 10 PSD. I should always read the titles here. This converts a power spectral density to octave format. The input array must have 2 columns, frequency in hertz, and amplitude in units squared per hertz. And in this case, we'll say we have acceleration in G. And let's do maybe a 1/6 octave band or 1/3. Okay, let's try 1/3. We'll do from 10 hertz to 500 hertz. We'll calculate. So by doing this 1/3 octave format, this is a power spectral density in 1/3 octave format. We have G squared per hertz, which is really GRMS squared per hertz. Then we have frequency in hertz, and you can see that it smooths out the data, especially at the higher frequencies. So that would be a 1/3 octave power spectral density. The overall RMS value should still be 1. Now we fall a little bit short just due to some imperfections in the way we convert the PSD into octave formats, but that's okay. Or if we wanted to, we could do 1/6 octave format, and not quite as smooth as the 1/3 octave format, but as a trade-off, we get a little better frequency resolution. Again, this is for white noise, so the ideal white noise would be flat horizontal line. And if we had a time, now this is only a 10-second time history, but if we had a 1,000-second time history, then it should smooth out quite a bit. But for our 10-second time history, this is okay. So that's just another tool that you can use within the package, the vibration data GUI scripts. You can calculate power spectral densities, and you can convert to octave bands. Then back on the slides, you can see for the data we had previously generated in the slides, again we get the really choppy power spectral density because our delta F is only 0.12 hertz, and we only have 2 degrees of freedom. And then an example in the slides, I converted to 1/6 octave format, and I did not superimpose the 2 plots, but if we just toggle from here to here, you can see how much smoother the 1/6 octave PSD function is. Okay, now we've been talking quite a bit about white noise, and actually within the vibration data GUI package we can also generate something called pink noise. So let's see what pink noise looks like. And we're going to have a 10-second duration, standard deviation of 1, and we're going to take a PSD with 1 segment, and then we're going to convert it to 1/3 octave format PSD. And by the way, everything I'm doing in this series, in this particular webinar, all these little exercises, please go back and do these yourself as sort of a homework exercise so you can get experience. So here's our pink noise time history, and actually I've applied a taper at both the front and back end. So we'll say this is acceleration in G versus time in seconds, and that's our pink noise time history. So we take the power spectral density, and then we convert to 1/3 octave format, so that's a 2-step process. We get G squared per hertz, which is really GRMS squared per hertz, versus frequency in hertz. And the slope here is -3 dB per octave. And that's characteristic of pink noise. And there's sort of a saying within or claim within the acoustic world, if you go measure the sound of ocean waves or waterfall, then some of those natural sounds will tend to have a pink noise type power spectral density, and that's kind of sort of somewhat true. Reality is always more complicated, but it makes a nice story to say, oh yeah, it's those things out in nature are just 1/3 octave formats. So now what I'm doing now is fumbling around with the slides here, and had a little. If you'll bear with me just a little bit, let's go to normal. So I'm going to kind of park this off to the side a bit here, and I just want to show you this. This will actually sort of be a review exercise. But one of the things we can do with our vibration data GUI package is we can do slope calculations. So we go to miscellaneous functions, dB calculations for log-log format plots, and we're going to do coordinates at separate frequencies. We've got a chi-square per hertz power spectral density. So let's just pick off 2 points from our PSD curve here. It'll be these 2 points. So we have 100 hertz. We've got 1,000 hertz. Our PSD at 100 hertz, 0.001. Our PSD at 1,000 hertz is the same except for 1 extra 0. So if we calculate, and this is the slope between 2 coordinates, then yes, in fact, we get our minus 3 dB per octave slope. And what that means is that just in plain log-log format, that means -1. So you can see, imagine these 2 decades here were evenly spaced in terms of how many millimeters or inches they each were. We would have a -1 slope here, just like a 45-degree type angle or minus 45 degrees. And we go from the top corner of 1 decade to the bottom corner of the same decade, except the upper limit. So we have the same decade. We go from the lower frequency upper amplitude limit to the lower amplitude upper frequency limit, and then that's a straight line. This also tells us that we have a 3.32 octave span from 100 to 1,000 hertz, and the drop here is a minus 10 dB change. So that's just another little thing you can do with the vibration data GUI package with that particular dB per octave utility. So let's see what else we have here. I think we're about ready to move on to another exercise. So let me get this to full screen mode here. So that's our pink noise time history and its corresponding power spectral density. So here's the Taurus automobile. This is my car that I drive. It's getting along in years now. It's got a few dents in the fenders and a few other blemishes, but back when it was closer to being new, this is what it looked like. And I did a little science project one day where I took an accelerometer and I mounted it in the console section. So we have this console section here, and I drove the car about 65 miles an hour down a highway. So with some imagination, imagine that I was an aftermarket of a vendor that wanted to create an aftermarket GPS unit that was going to be mounted inside this console, for example. So if that being the case, I need to know what the vibration input is going to be to that GPS system so that I can design and test it accordingly. So what I would want to do in that case is go out and take some field measurements, some accelerometer measurements. Now this was just a little science project, so I only had 1 accelerometer. But if I was doing this in earnest, for real, then I might have had multiple accelerometers, different axes, and I would have taken the car down different types of road surfaces, different speeds, different potholes, railroad tracks, rough roads, gravel roads, dirt roads, smooth highways, and done a real comprehensive test program. But this was just a Saturday afternoon in August, odd August Saturday afternoon in Arizona, and I just made it kind of a mini science project. But let's go with this, and we can do some practicing and learn a few things along the way. So this is a sample time history that I took. It's a 10-second duration along the x-axis, y-axis acceleration in g. This is for the case of 65 miles an hour down a highway. So what we want to do with this is we want to calculate the power spectral density function. And then that power spectral density function, we could use that as a basis for deriving a design and test level. So let's go back to vibration data GUI package, and first I'm just going to do a plot utility here. And I'm going to call in the time history, and that's going to be external ASCII and Taurus _ auto.dat. Now this file is also available on my blog, so you can download it and practice with it yourself. So let's see what we have. We have Taurus. I'll just say Taurus, and this is acceleration in G's. So we plot the time history, and then this is actually the same one in the slide there. So as we look at this, we want to sort of apply our critical thinking skills here, and what kind of signal is this, and what should we do with it? So we can do things, for example, we can just sort of zoom in and say, well, is it sine? Is it random? Well, it kind of looks like some broadband random, but there also looks like some either narrowband things or sinusoidal things superimposed on the data. Well, how do we resolve that? Well, in this case, we're going to resolve that via power spectral density function. So then I'm going to hit return here, and let's see, return again. So let's go to power spectral densities, PSD and spectral densities various, power spectral density, begin analysis, external ASCII, and I'm going to call up Taurus _ auto.dat. And then once I do that, I'm going to view my processing options. And actually another thing I'm going to do is I'm going to specify my plot limits. So I'm going to go from 0.1 hertz to 100 hertz. We can change that later if we want. Now, this is a critical decision-making point here. Wouldn't it be nice to have so many degrees of freedom and smooth the data? But this is one of those classic cases or occasional cases where we actually have some low-frequency peaks that we want to identify. So we want high degrees of freedom, but we also want narrow delta F. And we're a little bit torn, but we're going to sort of compromise in a way. I'm going to pick choice 2. This will give us 3 segments, 8,192 samples per segment. You can see the time per segment, delta F, which is the reciprocal or inverse of time per segment. We'll have 6 degrees of freedom, which is okay. We can do Hanning window. And actually, the way the internal calculation works is that it says 3 segments here, but actually there's going to be 5 segments because we're going to do a 50% overlap. So these segments are the number of non-overlap segments. We're going to calculate our PSD. We saw that time history flash by again. Cumulative RMS, we're not interested in. So here we are with our power spectral density, G squared per hertz versus frequency in hertz, for the Taurus automobile going down the road at approximately 65 miles an hour. So we've got some spectral peaks here we want to identify because we want to figure out what's going on with our data. We want to identify what the signals are, because if we can identify those, we can do a more intelligent job of determining what our test and design levels should be. So there's one spectral peak. It's kind of a broad peak, but it's about 1.52 hertz there. Then I'm going to do, let's see, I'm going to do create new data tip. Cursor on this peak. That's about 14.65 hertz. And then let's do a right mouse click, create new data tip. We'll go on this highest peak. This highest peak we have. So there we go, 29.3 hertz. And one thing we kind of want to notice, it looks like this 29.3 hertz is twice this 14.65 hertz spectral peak there. Now, this is part of our developing critical thinking skills, because this is just sort of a snapshot. All this is corresponds to a 10-second time window 65 miles an hour on a fairly smooth highway. So what happens if we were going at a lower speed or a higher speed? Would those spectral peaks shift around, or would they remain the same in terms of frequencies? So again, if we were doing this in earnest, we would do a comprehensive test program, and we could determine that all experimentally. But let's just go with this limited data we have now. And let's try and identify these spectral peaks, and then we're going to think whether or not those spectral frequencies might change as we go at different speeds. So what's going on with the 1.526 hertz spectral peak there? Well, it turns out that that is, imagine the car body as being a mass, and imagine the suspension system, the springs or struts or shock absorbers, as well as the tires forming a spring. So this is going to be the spring mass system of that automobile. Now, does 1.5 hertz seem plausible for a Taurus automobile for its spring mass frequency? So here's just a little table here showing that for a passenger car, its fundamental frequency, its spring mass frequency, should be 1 to 1.5 hertz typically. So it looks like the Taurus is on the upper edge of that. A sports car would have a higher fundamental frequency, and a Hummer, like a military vehicle, a Humvee, would have maybe 4.5 hertz fundamental frequency. Now, the reason the sports car and Hummer have higher frequencies is because control is more critical. So you can imagine the sports car, it's doing tight turns, it's going to high speeds, it's accelerating, it's braking, it's braking, it's turning, it's doing all sorts of maneuvers. So for the purpose of control stability, a higher frequency is needed. Then you have the Hummer going on all sorts of dirt roads, rough terrain, and there's even a greater need for a stiffer suspension for the sake of controllability. Now, for the passenger car that's just going to go at moderate speeds, moderate turns, hopefully, that can be a lower frequency. And of course, the idea here is to isolate. So we want to isolate. So as the passenger car goes over a speed bump or a pothole or railroad tracks, that the transmitted shock is minimized with respect to what the passengers will experience during that ride. Now, of course, there's some caveats there because we cannot allow the suspension system to bottom out because that could cause something to break or cause a high frequency shock to be transmitted into the body of the vehicle itself and from there to the passenger. So this is what we have, is we have our spring mass frequency for our automobile. Now, as the car speeds up or slows down, this should not change. I mean, there's obviously some chances for nonlinearities, but for the most part, we would expect that spectral peak to remain constant with frequency. Now, this is a very wide peak. Well, why is that? Because it's a highly damped peak. And there's something that we can do. It's called the 3 dB bandwidth method. So let's see if I can demonstrate that to you. And I may actually have to go back and go into the vibration data package here because I think I lost my plot or misplaced it otherwise. So begin signal analysis, power spectral density, and we're going to do, let's see, we've got an external ASCII, and this is going to be Taurus _ auto.dat. And we're going to view the processing options, and that was choice number 2. So we calculate the PSD. So now we're back to this plot here. So there's something we can do in MATLAB. I'll show you what this is. First of all, I'm going to go and identify the spectral peak there. So I've got 1.52, that's frequency in hertz, and then you can see the corresponding amplitude there. Now the next thing I want to do, that's a g² per hertz amplitude. I want to calculate what are called the half power points. So that's -3 dB, so that's going to be 1/2 the g² per hertz level. Now the points here are kind of coarsely spaced, so we're going to do something with our cursor here, and it's going to be selection style mouse position. So this will allow us to kind of interpolate the data And oops, I should have done one other thing first. I should have also done a create new data tip. So now this is going to be approximate, and that's okay. We don't need to be perfectly exact here. Let's see, what's about the half? Yeah, roughly there. That's one half power point. Then if I do another create data tip, come over here, and then I've got another half power point, somewhere in there. I guess about there. So these are the two minus 3 dB points. And if we take the frequency separation, so that would be the corresponding x value, this x value minus that x value. If we take into account the frequency bandwidth for these 3 dB points, and we take into account this frequency here, this 1.5 hertz, so we'll call that the center frequency, we can actually calculate the damping value. So if we go back to our PowerPoint slides here, and I've actually done this for this other set of data here. It's actually the same time history, and I'm not sure whether on this one I use the handing window or not, so it may be the same or a little bit different depending, but I've actually made this a linear x-axis here, so it looks a little different. The y-axis is still the g squared per hertz level, and in fact these points are slightly different, I think maybe because I did not use handing window in this case or something like that, but let's kind of ignore that for now. So if I take the 3 dB points here and take their delta F, that's about 1 hertz delta F there, roughly. And the center frequency is 1.526 hertz. We'll round that to 1.5 hertz. So the viscous damping ratio, or the modal damping, or you could call it the fraction of critical damping, is equal to delta F, that's the frequency separation, divided by 2 times, we'll call this the center frequency. So we have 1.0 divided by, in parentheses, 2 times 1.5. So that gives us a viscous damping ratio, 0.33 or 33%. Now, is that plausible for shock absorbers? Yes, it is. The shock absorbers provide isolation and they provide damping. And in order to have a stable control, a higher damping value is desired. You can imagine if you had very low damping in an automobile, you could go over a speed bump or a pothole, and you might actually get some resonant type response for the vehicle. So it's good to have damping to damp out its response, so you don't have that resonant type of effect occurring. Okay, now we've got a couple other spectral peaks that we want to identify. Now let's think about the tire. So, and I cannot remember what the model tire was. Let's just say it's 25-inch tire outer diameter. So please note the word outer here. So it's 65 miles an hour. Well, the circumference is pi d, so we have pi times 25 inches. That's equal to 78.5 inches. Okay, 65 miles an hour is equal to 1,144 inches per second. So if we take this speed, divide by this circumference, that equals 14.6 hertz. And then if we take a 2-time harmonic, that would be 29.1 hertz. So let's go back to our data. And it looks like, in fact, yes, we do have a 14.6 spectral peak there and a 2 times harmonic. So these two spectral peaks are almost certainly due to the tire imbalance effects. And the significance of that is if the car were going slower or faster, if it was going slower, these spectral frequencies would drop, or if the car was going faster, those spectral frequencies would increase. So it's important to know which of these peaks might be changing under different conditions. We'd certainly expect that change to occur. Now, I'm not sure why the error message is coming up. Let's go back to our GUI package here. I have to get out and get back in. Let's go to vibration data here. And we've got rotation, again miscellaneous. We actually have tire imbalance as an option. So we can say, okay, 65 miles an hour, diameter 25 inches. Let's calculate, and then you can see the 1 times and 2 times harmonics. So this little utility here takes care of all the unit conversion and everything, and it makes a neat and tidy way to do that calculation. So again, we always want to apply our critical thinking skills to data as we encounter our data. And let's see what else we have here. And that actually is going to end this particular course unit. So again, you have a new tool here. You can calculate power spectral densities, both for measured data and for data that we synthesize or make up ourselves. And certainly if you have any questions, you can send me an email. And I've got several emails that I monitor. But one that's easy to remember and they'll work just fine is tom@vibrationdata.com. And if you go to the website here, let's see, actually to the blog. And let me go to blog here. And for our webinar unit, this is unit 12. And you can get the PowerPoint slides here. Then here's also the Taurus_auto.dat file. You can play around with that yourself and go through the exercise we just did. And then you can also make sure that you have the latest and greatest vibration data signal analysis MATLAB GUI package. So in our next unit, we're going to be continuing to practice with power spectral densities. And we're also going to be synthesizing time histories to satisfy power spectral densities. And we're going to apply those base input time histories to single degree of freedom systems to see how they respond as well. So I hope you've enjoyed this course unit, and we'll see you next time, and have a good day. So thank you and goodbye.